Alright, so it is fiddling around a little bit. And I wrote this little program that computes the digits to the fundamental circle constant, which, if you're at all familiar with me, is not pi. Pi is not the fundamental circle constant. Fundamental circle constant is 1/4 of that. And among the many pieces of evidence for this is that most of the methods for finding pi, for computing it precisely, are actually finding pi on 4 in the first place, and then you artificially multiply it by 4. So like this method here, what you would do is you would take your result and multiply it by 4. If you leave it alone, it's the fundamental circle constant. The fact that everybody has to go back in and just artificially multiply it back to by 4 to get pi, that's a sign that it's not right. Anyway, so yeah, most of this is the basic approach here. I don't even understand how this was derived via Taylor series. This was given to me. I just found this. I'm sure I can make sense of it if I needed to, but I don't need to. And it's an alternating infinite series. If we were totally faithful to what's going on here, this would be like this. Alright, so it's the inverse of the nth odd number times x to the nth odd power, where x is 2 or 3, and both of those two series then get added together. So yeah, you get all of this. And with a little bit of algebra magic, I reduced that down to this. Well, this. That MPF thing is to make it so that I can go out to arbitrary precision, which works pretty well, although it bogs down severely past about, well, really much past 1,000 decimal places. So this will run in about, well, yeah, less than 1/10 of a second. It'll give you 1,000 iterations, and then it does about 60.25% of that will be decimal places. So out of this, you're getting like 600 to 603, somewhere in that ballpark, decimal places. So fiddling around, like figuring out how that all works, I used that to truncate the precision that it's computing at, so that it's not handling a bunch of extra crap that it doesn't need to. And even still, so if I drop in another 0 here, so that took less than 1/10 of a second. Here, if I drop it down to 100, you'd think it'd be about 10 times faster, roughly. And that's fairly close to accurate. If we drop it down to 10, it's roughly 10 times faster than that, right? So you'd think as we scale this up, it's going to do something close to that. Like, it's clearly not doing exactly that, but it's close. Because there's some things occurring. There's some overhead occurring that's not going to be scaling exactly that way. But watch what happens when I bump it to 10,000. This is real time. The recording did not freeze. It is actually it is actually taking this much longer. So you'd think based on this that it would take maybe about a second. If things are really bad, maybe 2 or 3 seconds. No, it takes, in this instance, about 34 seconds. Previous runs, I was getting about 31, 32 seconds. So there it is. There's about 6,000 decimal places of the fundamental circle constant. And at some point in here, I think it's actually right there. I think that's the last. Up to the 630. I think this is wrong. So if I go up to the next step, we can actually see that. And again, it'll take about probably another 34 seconds. And I'm not entirely sure why it bogs like that, but I have some ideas. But it gets far worse. It grows far worse as you scale up from this point. Yeah, just 50,000. So this was 10,000, and it took like 34 seconds, about half a minute, right? Yeah. So 630, yeah, right there. So this one is probably added on another, like that digit is probably correct. So actually, this 4 that I put on here is actually a buffer, just to make sure that there is enough extra precision in there that you are getting out that far correctly. But we don't really need much further than that. And this seems to work really, really well, as far as I've tested it. But I've only tested it out to about 30,000 decimal places, because so that was with 50,000 as this number, and that took an hour and 8 minutes. And it's only 5 times as many iterations. So if it's scaled nicely, you would think, well, that'd be like 2.5 minutes, maybe 5 minutes if things are going poorly, 10, 15 minutes if things are going really poorly. No, an hour and 8 minutes. Yeah, and so like I dropped in right in here. I dropped in a line like this, just so that I could see. So M is the counter that I'm using, just so that I could see where it's at. And initially, it just rapid fire. It's reading like it's a blur. You can't read any of the damn numbers. At the end, it's like dumping out like one number, maybe every quarter second. So you can very clearly read every single number as it comes in. It's like, it really, really bogs down. And I think that's related to something like paging, or God knows, something with the way the memory is being handled. I mean, it's still working. But I think it's past the point where it can be hardware accelerated, because the numbers are just so big that it has to go into awkwardly into slower sorts of memory devices. But it does work. Yeah, I don't really have anything terribly interesting to say about this, other than this is basically it right here. So this is taking your index and turning it into the next odd number. And what I've inlined the addition, the terms that are added and subtracted, right? So those pairs, each of those pairs, it's basically being reduced to one term. And that saves you a little tiny bit of overhead for You don't have to do that loop. It kind of depends how it's handled, but this is it's Python, so it's a scripted language, so there's probably not much optimization there. And then here, this is actually the 2 squared and the 3 squared. I just wrapped it up right there. The 2 and the 3 start off here, and then these are made into high precision floats, so that they're this big. They're this precise. I don't know that that's actually necessary. Because out to something like 100 iterations or so, it really didn't seem to be, but out here it probably starts to be. I'm not sure. So basically what's happening here is we're using the way that fraction addition works, right? So basically, I'll just comment it in right here. So what you're doing is you've got, like, we want to add this thing to this thing, but those are fractions for each term. It's a fraction, right? So it's 1 over something for the 2, and it's 1 over a similar thing for the 3, right? So 1 over A plus 1 over B is, and note too that you've got like the 1 or the 3 or the 7 or whatever, right? So there's like another part in there, right? There's something like that, right? That's shared between them. Right. So what you're going to get is that 1 on A has to be multiplied by B on B, so you're going to get this. And then that 1 on B has to be multiplied by A on A, so you're going to get this. So you're just going to end up getting A plus B on A times B. And you're going to also get that shared other factor. And that's exactly how this was written. It's just your A is K2 and your B is K3. And I basically kept those names there. And that way you don't ever have to deal with actual exponents. You don't have to deal with powers of anything if you manipulate stuff right? So if you notice what's happening here with the K2 and the K3, as we're stepping through everything, instead of finding an exponent, taking an exponent separately each time, I'm just growing it along as we walk through it. So at any point, I'm only multiplying by 4, right? Because, if I take 2 to the first, and then 2 to the third, and then 2 to the 5th, and then 2 to the 7th, right? That gets hard. As your exponents start growing, you're starting to have a real pain in the ass going on. But if I just take whatever the hell I have from the previous session and I just multiply by 4, and then the next time I multiply by 4, and then I multiply by 4, and then I multiply by 4 as we step through, well, what's going to happen is this step, so let's say that x is a 2, right? As I go from an exponent 3 to an exponent 5, all I'm doing is multiplying this by 4 to get there. Or if it's a 3, then I'm multiplying it by 9. So that's what these terms are. Right? And then the subtraction one is 1 further up, so it also gets it. But I'm doing it like right after. So initially it's going to get a 2 and a 3, just a clean 2 and a 3, and then it's going to scale that up, and then it's going to execute this, and then it's going to scale it up, and then it's going to loop around, execute this, then scale it up, right? So it just keeps coming through here. And yeah, so this is the number of indices that we're dealing with. That is true, but we're actually only stepping through every other one because it's getting doubled here. Yeah, It just ended up making more sense that way. So we end up being able to do all of this crazy dealing with exponents and shit with just simple multiplication, addition, and subtraction and division. Just basic arithmetic. So, I don't know. I thought that was relatively clever. That I was able to reduce it that much. I'm sure I am by no means, like, unique in this. This is not really the kind of programming that I've ever really done much of before. So, I'm sure there's lots of optimization shit that I'm not aware of and I'm not doing and whatever. But just getting it this far, and I saw speed improvements when I, did this. Yeah, I thought that was pretty cool.